Hello everyone, we are Group 18 and our project is GPMS, a Generative Projection Mapping System. Welcome to our midterm demo. My name is Francisco and I am a computer engineering major. Declan and Victoria are also computer engineering majors. First, we will run through a GPMS parts overview, which will include all the parts and subsystems within our project. Next, we will show you our project demo. Finally, we will show you the engineering requirements that our project will adhere to, and we will emphasize 3 of those requirements that we have demonstrated to you in our demo.
GPMS is your Generative Projection Mapping System. GPMS is a system designed to transform any physical structure into a canvas for AI-generated art. It consists of Raspberry Pi 5 connected to a touchscreen display, projector, and camera. The user starts by calibrating the projection area via software and aligning the projector's field of view with the target structure, as shown in the animation above. Once the alignment is complete, the system captures an image which is then sent to our custom generative AI server. The server processes the image and generates a stunning AI image that aligns with the key vertices and edges of the captured structure, as demonstrated in the animation below.
First, we present 2 hardware parts of GPMS. The touchscreen monitor, where the user will interact with GPMS and provide our system input, and the projector, which will project our system's output for the user to see. Next, we present 2 more hardware parts of GPMS. The Raspberry Pi 5, which is the brains in charge of facilitating GPMS, along with the power bank to power this Raspberry Pi with the optimal power ratings and voltage protection that it provides. Next, we present the last 2 hardware parts of GPMS. The camera module, which will be connected to the Raspberry Pi 5 via serial camera interface, tasked with capturing image structures. On the right, the server, which sits in the Draco lab here at UCF, where users will send text prompts via our user interface and receive a selection of AI-generated images back. Finally, to assist in hardware integration and better provide portability and compactness to users, we included a hardware subsystem enclosure. This enclosure will be mounted on top of the projector and house the touchscreen monitor, Raspberry Pi 5, and camera module. On the top, the monitor will sit flush into the enclosure at a 13-degree angle for users to interact with in order to avoid glare. Then the monitor's micro HDMI cables will connect to a 90-degree angled HDMI adapter that will then connect to the Raspberry Pi 5 in the layer below it. Here, the Raspberry Pi 5 will stay intact due to the screws at the bottommost layer. This will ensure that the Raspberry Pi 5 is safe and secure right where it needs to be. Then this Raspberry Pi 5 will connect to the camera module via serial camera interface and will be intact on the back face due to the holes for the camera to screw in. This camera module will sit right above where the projector lens is. The power supply will connect to the Raspberry Pi 5 through the front opening via USB-A to USB-C, as it all sits below the projector in order for a light mount and releasing any excessive weight on our projector. Now, regarding the software parts and subsystems of GPMS, here we present the GUI, which is what the user will interact with at the click of a button. Then the user will walk through a series of pages. The user will have to read a few steps before they begin their vision. Once they understand their task, they will proceed to the calibration page where the camera turns on and they will pick 4 vertices to capture their structure. Once the structure is captured, they will proceed to the sensitivity page where they will leverage canny edge detection to fine-tune the structure's edges to their liking. After this, they will input their prompt in 1 to 2 sentences that describe what they are looking for in their final image to be projected, thus sending a request to the server. Next, the server will return a selection of AI-generated images in response to the user's prompt, and the user will then select that image to be projected. Finally, the user will see their targeted structure from earlier with the AI-generated image projected onto it. Here we present OpenCV and Stable Diffusion and how they both work alongside each other in GPMS. Together, they work to capture, process, and generate images based on a structure. The device will first use OpenCV to capture a structure via camera to detect the features of that structure and then allow a user to input a creative prompt into the deep learning model, Stable Diffusion, describing how they want that structure to be transformed. Stable Diffusion uses this prompt to generate an image based on the detected structure, projecting the prompt's elements onto it. The final result is a combination of the original image structure and the artistic transformation. Here we present our server. Our API module opens a designated port on a Python server to handle post requests from users to the server for image generation. It accepts a prompt, which is the user's vision, and an image capture, which is processed via OpenCV from the user structure selection. Then Stable Diffusion is used with control nets to generate AI images. These control nets ensure that the generated images respect the structure of the input image while also incorporating the user's prompt. The server processes the request and returns a selection of AI-generated images to the client, providing multiple variations based on the input.
Picture this. It's the night of your Christmas party. Your apartment looks, well, ordinary. Those sleek modern art pieces that usually fade into the background aren't exactly screaming festive. You want your space to dazzle, but time's ticking, your artistic skills are questionable, and you're craving a high-tech solution. Enter GPMS, the Generative Projection Mapping System. Imagine turning your entire living space into a winter wonderland in less than a few minutes. Step 1. Setup. First off, set up the projector and connect it to the GPMS device. This is your canvas for creating holiday magic. Now, begin navigating the GUI by first reading the instructions on the main window. Step 2. Projection area calibration. Then, use the GPMS software to select the edges of your projection area until you are satisfied and can proceed. This helps calibrate the camera and tell GPMS exactly where it can paint with light. Step 3. Adjust threshold values. Here's where you can fine-tune your decoration. We'll adjust the threshold values and observe changes in edge detection. This step determines how closely the new image will match your room structure. Want your decorations to follow the lines of your furniture, or prefer them to be more freeform? You can control that here. Step 4. Input your vision. Time to tell GPMS what you're dreaming of. For our Christmas party, we might input a Christmas theme with candy cane frames and gingerbread windows that look out onto a winter wonderland. This is where you let your imagination run wild. Step 5. Generate and refine. GPMS will now generate a series of images based on your input. Don't love what you see? No problem. You can either tweak your text input or adjust the sensitivity thresholds we mentioned earlier. Keep refining until you find the perfect holiday look. Step 6. Project and enjoy. Found an image you love? Great! With a simple click, we can now project it onto your space. Just like that, your room is transformed into a winter wonderland ready for your Christmas party. GPMS is a versatile tool for any occasion or mood. Whether it's a spooky Halloween gathering, a summer beach party, or just a cozy night in, GPMS can help you set the perfect scene with ease. Now, let's dive into the technical aspects of GPMS by demonstrating 3 key engineering specifications. These metrics are crucial for understanding the system's performance and efficiency. As you can see, we have several categories of specifications. Size. Our target dimensions are 7 by 10 by 8 inches, ensuring the device is compact and portable. Weight. We're aiming for a weight of less than 10 pounds, making it manageable for users to handle and transport. While these specifications are important for the overall design and usability of our device, today we'll be focusing on measuring and discussing the last 3 specifications highlighted in yellow. First, elapsed time. Our target is less than 5 minutes for the entire process. 2. Alignment accuracy. We're aiming for less than 8 millimeters of offset from our projected image. 3. AI generation time. Our goal is less than 1.5 minutes per image. These 3 metrics are crucial for ensuring the efficiency, precision, and speed of our GPMS device, which directly impact the user experience and overall performance of the system.
Our first metric is elapsed time, with a target of less than 5 minutes. This measures the total time from setting up the device to projecting the final image. For this demonstration, we've conducted 10 test runs, recording the elapsed time for each. Our test procedure involves starting a timer, setting up the projector and GPMS device, calibrating the projection area, adjusting threshold values, inputting a vision prompt, generating and selecting the final image, and projecting it. As we can see from our results, the individual run times ranged from 1 minute and 13 seconds to 1 minute and 37 seconds, with a mean time of 1 minute and 24 seconds, excluding AI generation. The standard deviation was 7.64 seconds, indicating consistent performance across runs. When we factor in AI image generation time of 3 minutes, our mean elapsed time increases to 4 minutes and 24 seconds. This is still within our target of less than 5 minutes, demonstrating that we're meeting our specification for this metric. Our next metric is alignment accuracy, which measures how precisely we can align the projected image with the target surface. For this demonstration, we conducted 10 test runs. In each run, we measured the alignment accuracy at 4 points on the projection surface, recording the deviation in millimeters from the ideal position. Looking at our test results table on the right, we can see the individual measurements for each run. The accuracy for each run, shown on the left table, is calculated based on these 4 measurements, with lower numbers indicating better accuracy. Our target is to achieve an accuracy better than 8 millimeters for each run. As we can see from the average accuracies column, all of our runs met this target, with average accuracies ranging from 0.75 millimeters to 2.75 millimeters. The average accuracy across all runs is 1.725 millimeters, with a standard deviation of 0.6175 millimeters. This indicates that on average, we're significantly outperforming our target of 8 millimeters, and our performance is relatively consistent across runs, as seen by our standard deviation. While we're at the halfway mark of our project, we'll continue to refine our system for even more consistent performance. These findings provide a solid foundation for precise image projection in our system, meeting and exceeding our initial expectations. Our last metric is AI generation time, which measures how long it takes for our AI model to generate a single image and return it. However, it's important to note that at this stage, we only have data on the time it takes to generate the image, not the time to send it back to the user. For this demonstration, we conducted 10 test runs, measuring only the AI's image generation time. Our target is to generate each image in less than 1.5 minutes. Looking at our results, we can see that our generation times for each run range from 42.6 to 43.4 seconds per image. The mean generation time across all runs was 42.9 seconds, with a standard deviation of 0.23 seconds. These results show that our AI generation times are significantly faster than our target of less than 1.5 minutes per image. The low standard deviation indicates that our generation times are highly consistent across multiple runs. While these results are promising, we need to keep in mind the fact that total time for image delivery will be longer once we factor in the time to send the generated image back to the user. This will be an important consideration as we move forward with implementing the full system. Thank you for listening to our presentation. For more information, visit our website.